I'm a chemist. I work for Argonne. My name is Alvaro. Well, I want to acknowledge people before I run out of time. So first, my colleagues, Jackie Cole from University of Cambridge, my postdoc, Ganesh Sivaraman, and Marta, who really worked after hours to have this event that make this happen, right? So I really witnessed that she read each of your packages, each of your CVs and recommendation letters, and she fought against committees to have you here. So just 3 minutes ago, I finished my parental leave. I took 6 weeks of vacation, no, of parental leave. And my summer project was trying to catch up some concepts with my daughter, my baby daughter. And basically, the conclusion was like, let's try to make any problem a machine learning problem, right? So I really like that idea, and I hope probably this is something that in the future all we will try to do, make the computers to work or the machines to work for us, right? I know. So I don't know if I had to sell this to you. Now we are in a stage where practically we can make science from data. So probably 300 years ago, people were doing experiments to figure out why the nature behaves as it works. Then with Newton, Leibniz, etc., the scientists start to do equations, right? So to try to predict or try to describe what was happening. And in this century, computation helped, to solve very complex problems. And probably in the last decade or 2 decades, now we have this conjunction between experiments, theory, and computation, and that produces this new science that is the data science, right? So this is, now we can get insights without, or with all the previous knowledge, right? So I'm a chemist, and I'm very worried of trying to find new molecules and trying to find the correct substances that produce new materials. Really, the space, the chemical space, right? All the combinations that we can create with the atoms we know, it could be huge. This space, some estimations say, could be, we can create 10 to the 60 molecules, which is an impressive number, right? So if we count the number of molecules of water that are in the planet, my estimation say we can find 10 to the 40. So trying to find the correct molecule in these spaces a huge effort, or a huge challenge. Even some estimations recently say that this number is incorrect, that it should be 10 to the 180 combinations. And what we know of this space, so there are data sets, for instance, for experimental studies where companies start to collect all this information, and they more or less have 10 to the 8 systems. Computationally, probably we have more systems, right? Because we just can create whatever we want in the computer. And so one of the most relevant data set that exists is the Harvard Clean Energy Project with 10 to the 9 calculations. So for instance, just to give you a snapshot of what's happening in this field, so this is the CAS registry is a huge data set of experimental molecules with experimental physical properties. And every year, they add 10 million systems more, right? So I don't know if this is really useful, probably it is, but we haven't solved the most urgent problems yet, right, for health or to solve problems for materials that are smart or etc. So really we are just accumulating, and we need also to process all this data. Also, if you see, we have an increase of publications, right? So the stock is not cheap anymore. So every year we add thousands of papers. We accumulate all this data, and not necessarily. So now, if we want to search or do literature search, we have to navigate among thousands of papers. In the other hand, we have the problem that the computation is not going faster as our discovery of experiment is, right? So now we are struggling if we want to just to compute and do first principle calculations or quantum chemistry calculations. So we have, I think we have to start to learn from what we compute in the last 40 years or what we have seen in the last 100 years. Actually, I really like this plot. This is the number of bases, nucleic bases in DNA, so genes, right? That can be sequenced in one day, right? So now we are in order of trillions of bases that can be sequenced in one day, right? So experiments actually are going faster than the density of microprocessors we can get in computers. So computing computing is not enough. I think data science come to help here, right? And well, lately I've been working in projects related with energy. If more or less the needs for energy nowadays is about 18 terawatts per year. This is, I don't know, yes, it's a huge number, right? Just think that this is all the energy that all the Earth, all the population needs in 1 year is 18. Just keep that number, right? In the next 30 years, we will have to almost to duplicate that figure. And in the next 80 years, we will have to almost, again, to triplicate the current number. So the challenge is huge. We need a lot of energy. And the problem is that renewable resources, well, we can keep burning fuels, like fossil fuels, and we will run out sooner or later. The problem is that if we sum all the renewable resources, like wind, geothermal, or biomass, this will not satisfy our energy needs. What comes to help is the solar energy, which practically is infinite, right? So even the technical value, so because if we cover unpopulated areas of the Earth, we can get even 10,000 terawatts. So and the energy starts to become cheaper and cheaper and cheaper and really competitive against gas, right? So in the 70s, it was almost $70 to produce, it cost $70 to produce 1 watt per hour. And now with solar energy, and now we are about 10 cents. So to really beat fossil fuels, we should go by 0.08, right? But we are almost there. So the problem is that all these technologies are not efficient yet for mass consumption. I really like this plot. This shows which sectors are consuming more energy in our lives. Residential is 20%, commercial 18%. But what I I want to highlight is that the static, right? So what is static is almost 70%, right? So the transportation is what they say is moving, right? So is this sector that is moving, but so where we have to carry the energy with us, but the static one is where we can put solar cells, right? Fixed on the roofs or something like that. Also, so electricity and housing is also producing almost 70% of the carbon footprint. So I think this is where we have to tackle yes, the problem, right? So trying to produce more energy, more electricity with solar. And well, we have seen in many places solar cells. Probably some of you already have roofs with solar cells. Satellites, so I think since always, they have solar cells. So practically every time you use internet, you are using solar energy. And in some cases, solar cells can be functional, right? So like roofs or even walls, right? So if you went to Millennium Park during these weekends, there is a theater called Harris Theater in the north part of the park, and so the walls of this building actually are solar cells. So so I really like that idea, no? So solar cells as functional, and well, this is a chart of the multiple families of solar cells that exist, and against the efficiency, right? So the best ones are the purple with triangle, the three-junction, multi-junction cells. And then we have silicon and some emerging perovskite cells, photoelectric, which included the perovskites and sensitized cells, which are in the lower part, in the orange lines, which are not super efficient, but are super cheap and really they can be even organic, so they might not be a burden for our health and our future, right? So I went last year to Lausanne in Switzerland, and I found that this convention center, they have a solar cell that is a window, right? So it's a window. So it's a substance that is imbibed between two glasses, and you can see through. So it's transparent, and can produce electricity. So I think it's really neat. I went closer to see that it was actually a wire. So I know it was just a fake, and I took a selfie, right? So no selfie, no glory, right? So this technology works like this. So you have two glasses, and inside you have an electrolyte, and floating in the electrolyte you have spheres of titanium oxide. So everything you see white, even the toothpaste and the glazed donuts, they have titanium oxide. So it's a material that has a really huge reflection factor, right? So it's extra white. And these spheres are tinted with a dye, right? Organic dye that absorbs light. Right? So this is the ground state of the dye. When it absorbs energy, the electrons are promoted, to an excited state, and then this electron is like water, right? So you increase the flow, and the electrons start to jump, right? So jump to the titanium oxide material, and then it's transferred to the glass, and then the electron travels to the other side of the other side of the electrode, and then it jumps to an electrolyte that goes back to the dye. So So all this movement of the electron produces work and electricity. The most efficient ones, cells, are made with metals, so are not ecologically friendly, but are the most efficient, are like 10% efficiency, compared against 20% of the solar cells that we can install on our roof. The problem of the dyes that we can put here is that everything you see in color in this room has a dye. And all these dyes might produce electricity, but we don't know which one, right? So it's a huge problem. And also, so this, the energy levels of this dye should be between the oxidation and reduction potential of the liquid, right, the electrolyte, and above of the conduction band of the titanium oxide. Also, these dyes should cover most of the solar spectrum, right? So we want to be very active when the sun is in the zenith, right? So at noon. And so the parameter we're looking at is the this AM.5, right? That is yeah. So this is a parameter. So it's the lights of the sun at noon in the zenith in the equator. So also something that we might like is that this dye might be combined to cover most of the solar spectrum. So the project, so what we wanted to do is to take molecules that exist, no molecules that we just draw in, or we can draw in a paper. So we went to the websites of this American Chemical Society, and we started to download papers. Don't do that, because they blocked us. Actually, they closed the access to Cambridge. Then we had to sign a contract to be able to run our Spider, downloader. And we took all these papers, almost 400,000. I don't know how long it takes you to read a paper and extract all the information, but we did this for 400 papers, right? And then we put everything in Excel tables, and then we start to run calculations. So we follow a funnel approach where each filter reduces one order of magnitude. So we start with almost 100,000 substances, and in each level, right? So just by looking at the system, oh, this is too big, we remove it. Oh, this doesn't have any optical activity, we remove it. We cannot compute this, we remove it, right? So we ended with only a hand of them, right? So only with 10. Obviously, we didn't do this by hand, so we didn't open the paper and try to find the quantities, right? So to put them in the table. So we use machine learning for that. So my colleague Jackie Cole, she's a developer of ChemData Extractor, and what it does is transforms text in vectors and then annotates each of the elements as a noun, as a verb, as a adverb. Yes, if you have a mark or something like that, like parentheses or periods or whatever, you start to annotate them, and then we use natural language process to track, first to distinguish what is, for instance, a chemical composition, and if there are acronyms, and then start to create a connectivity tree, right? So figure 2, red, so start to connect all the dots, and then finally we got that the system A with this name and this formula has this property, right? And we then pass everything to unstructured databases like Mongo, because some of this information is missed. So this is not all the papers have the same quantity of information. But then having all these dictionaries, we create these CSV files. Now with the name of, or the chemical, just with the name of the chemical compound, we create the chemical formula, carbon, 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 NO, whatever. And then from that, we create chemical objects that we compute with quantum chemistry calculations. The result of that is that we ended with 5 systems that we thought were awesome, right? And then we went to the experimentalist, and the experimentalist say, well, yes, you can compute thousands, but we can do only a few of them. So they confirmed that they were good because they came from the literature, and then they start to mix and match them, and they found that X26, don't ask me for the name, but it's too long, plus then molecule number 15, both could work together, to create, to cover most of the spectrum of the sun, right? So this is called panchronism, right? So the one is too blue, probably the other is too red, so combined, it creates a really good dye. And what it was awesome is that this combination beats one of the most efficient organometallic dye. So this is, so we beat, we beat the best no organic dye. So I think it's an awesome result. And then, well, we start to do machine learning beyond the extraction of the data. And something I really like, because we don't have millions of points, I did Gaussian regression. So probably you are too advanced. You must know that you have 4 points, and well, you can pass a line among them, and you have a linear regression, or you can just connect them. And obviously, neither of these two are good approaches because this is underfitting and the other is overfitting. So to get the best function, probably you have to pass something like this is smooth, and this is what Gaussian process does, right? And not only that, once you have your new point, right, so you want to predict the value of this new point, it gives you a mean, right, a mean value, and also the standard deviation, right? So this is, I really like Gaussian process for that, because you get the mean value and also how bad is the error. If you don't know, I go quickly through the explanation of Gaussian process. You have a y function that you have a target function, right? And that you don't know. And what you want to do is to propose an f function that is similar to this y function, but you have to add some noise, right? So you don't want to overfit. And this is this noise. Yes, it has a Bayesian, theory behind that explains the probability of this estimation. And what you have to do is, solving all these equations, you get, so what you have to do is, so to create this mean function, you need a covariance matrix. This covariance matrix has the shape of a Gaussian function. So, and these elements inside have how different are 2 points. So to create this matrix, you have all the points that, so you compare all your data, and then when you have a new point, you can, that is unknown, you have this, I mark with asterisk, you can also compare the unknown with the known, and so finally, what you get is, this actually is a sum of Gaussian functions. So because all this, this gives you a vector, right? So this is the matrix. So the invert, yes, is the inverse matrix of the matrix you know times the matrix with element you don't know plus your mean function, and you get the estimation of the point that you want. Sorry, I'm trying. I have to practice for this explanation. But essentially, you have your function as a sum of Gaussians, right? And the most difficult part is to invert the matrix that you know. So a problem here is how to compare two systems. So if you are a chemist, probably it's difficult to compare two molecules. So how to have a metric to say water is different to methane, or alcohol is different. This alcohol is different to another alcohol. So one way is to describe the thing as vectors, and then what we can do is to measure the distance between these two vectors, right? So so there is called molecular fingerprints that. There are handbooks of them with thousands of those systems, of those fingerprints. One I really like is the Morgan fingerprint that describes each element of this vector as a fragment of the molecule. Having that, and all the experimental values and theoretical values, I got really good predictions to predict the color, right, of the molecule. And I'm really happy with this number. We have an R square of 86.86. But we remember that the dyes have two aspects. One is the color, and the other is how intensive is the absorption of that color. And I couldn't get a good prediction for the intensity. This is only the color. For intensity, I couldn't. But what I could do is predict how intensive it is. Not the exact value of the intensity, but I split my system in very intensive and not too intensive, and I could predict if a molecule is really, really intensive in the absorption. So if you give me a name of a molecule, now I can give you the color, right, with my data set and my Gaussian process, and I can tell you if it's absorbing very, very intensive. Well, this early today, we had these amazing presentations about generative models, and something that I really would like to do in the upcoming months is to use my data set to produce new dyes. So I work with only dyes that already exist, but I want to produce new dyes that could be chemically stable, so we can produce them in the lab. And this is for the future, so I want to use generative models. And also, something that we want to do is to take all these tools, make them public, so everyone can play with them, and apply the same for other projects like drug discovery or something like that. Well, thank you so much.